I'm Pamela Lombardi, for those of you who I don't know yet. Pretty much, again, I guess the order of events is actually really helpful because everybody talked about biology, and then we start talking about molecules interacting with things. And so what Leota was talking about was basically having some molecule that's kind of a target. And then you do a lot of reactions, you solve this big reaction scheme to get to that target. What my interests are a little bit different, where I actually like to do methods development, where I work on one specific reaction with the idea of either coming up with a new reaction or improving an existing reaction. And in particular, I like to make chiral things. So for those of you who like stereochemistry, you don't even have to love stereochemistry like Argo 1. But the idea that we can actually do a reaction and control the stereochemistry of a reaction is the part that I find really fun. So pretty much most of you are, or I think almost everybody here, we have a few first years in the room.
They're all gone.
They're all gone?
They're all gone.
Oh man, okay. You guys know about enantiomers, so non-superimposable mirror images, just like your hands. And one of the things that you guys are probably used to is we actually can basically show you chiral molecule stereochemistry, and then you have to keep track of every of your reactions in order to. A lot of people never know this really acutely right now. So one of the things that's true though is we can actually make chiral molecules from molecules that are not chiral. So we call those prochiral molecules. For example, we have this cyclohexene, and at this position we can do a radical halogenation on the twist around. Using bromine and light, we can actually get both enantiomers out. So when we do a reaction that does not have anything chiral in it, we're going to get a mixture that is not optically active, although we are creating stereocenter in each of these reactions. And another reaction that does the same exact thing is bringing addition to ketones. You guys will know this in a few weeks if you don't know already. But the same idea here, we're starting with molecules that do not have any chiral centers. And once the addition is complete, we have new chiral centers generated. But once again, we're getting racemic mixtures in each of these cases. And so these are standard conditions, and just to kind of remind you guys, again, might be like this one, about the way that we actually get both enantiomers is we're usually going through some intermediate, either in symmetry, or it has some either plane of symmetry or it's planar. And in this case, you can imagine that the intermediate in this reaction is actually a radical, which is flat, and bromine can either be added from the top face or the bottom face, and that's how we actually get the chiral center into the molecule. But again, because this molecule does not care if it's coming from this face or this face, we're going to get a 50-50 mixture every single time. So another reaction, and the reason I'm putting this one up, and you don't have to remember all of the reactions, is that there are other types of reactions where you can do similar things, and one of them is called allylic oxidation. So the allylic position is the carbon that is adjacent to the double bond, and upon oxidation we can get an alcohol group here. And allylic alcohols are pretty interesting, partially because of the fact that they can be used as building blocks, but they also exist in many chiral molecules that are of interest. So this one here is Taxol. Believe it or not, this is a natural product. It's found in the extract of a tree, but it is a very, very potent anti-cancer drug. And for many years, there were lots of efforts put towards making this molecule, as well as actually isolating it, but it's so rare that natural sources make it difficult to actually get exclusively from just extracting it from tree life. So what people did was they made it. So the first photosyntheses were published almost simultaneously in 1994. Holton actually started doing this work in 1982, and you can see the structure. It's pretty crazy, but it's a molecule that exists in nature, which is the cool part. But what I really want to point out here is that we have allylic alcohols present in this molecule. And since a lot of pharmaceutical drugs, we want them to be enantiopure, finding ways to get stereocenters that are just R and not S, for example, is really, really important. So how do we get one enantiomer? So we have this reaction, and we're like, we don't want that one, we want this one. There are a couple ways that you can actually do this. So the first way is something you guys have actually done. If you took Orgo 1 lab here, or if you're about to take Orgo 1 lab, what you can do is you can start with racemic mixture. So you guys did this with the amines, and you added tartaric acid, which is a chiral molecule, and you separated them based on their physical properties. But the problem with that method is that if you have this very important molecule that might be very precious to you, you're pretty much throwing half of it away every time, so you can only get 50% out. So you start with a racemic mixture, after the resolution, you only have half of what you start with. So another way to do this would be the use of an anti-selective reagents, where we have a reagent. This is based on some of my PhD work. And so you have some sort of reagent that has chiral centers on it, and then you do a reaction and you get a chiral product out. But the problem with an anti-selective reagent is that you're using a stoichiometric amount of your chiral substance to get your product. So even though they're very valuable, and a lot of these methods are very useful, and sometimes you can recycle the chiral material, you would still like a way that maybe you wouldn't have to use so much chiral material, which generally are relatively expensive unless they are sugars or amino acids. And so the way that I like to do these things, or think about these things, and many other work as we put toward this, is an anti-selective catalysis. So using a catalytic amount of a chiral molecule instead of a stoichiometric amount. And so the reaction that we've been working on this summer, this is not the one we specifically used, but this is stuff that is done in the past. You basically have an oxidant, so we're doing a Lillich oxidation, and then we have our cyclohexene. And the molecule, or one of the chiral ligands that have been used previously, is this. So this is a bisoxazoline ligand. And so pretty much what happens is you get 80% yield without the ligand, but you get a racemic mixture. But you can do this with only 5% of your copper catalyst and or this ligand. So only 5% relative to the amount of cyclohexane or peroxide that you put in. And you can actually get the reaction to go, but some major problems with this reaction is that it takes 21 days, you get 43% yield. And this selectivity is okay. So an ER is basically the ratio between an enantiomer. So you get 90 to 10 R to S. And so what we're doing is we're developing new ways to do this. Nobody has done this reaction yet with N-heterocyclic carbene ligands. And some people have used amino acid-like ligands, but nothing similar to this. So Ryan has worked on making some of these ligands. And Nisha this summer worked on these ligands. These ones theoretically should be easier to make than these, but research tells us that that's not necessarily the case every time. So anyway, I'm not going to fly through this mechanism really quick, but my point is, because I know I'm running out of time here, is that when we're doing the reaction normally like that radical I showed you before, you can imagine that the peroxide could add to either the top or the bottom face, just like we did in the radical normalization before. But when you have the copper present, the copper is actually going to link up with that radical. And if you have a chiral ligand attached to your copper, the idea is, with an anti-selective catalysis, is that the ligand will actually coordinate to the copper and create an environment around the molecule that's reacting that will only allow reaction on one face and not the other. So what you can do is you can use something that's chiral to influence whether the reaction goes on the one face of the molecule or the other, and therefore get an anti-selective reaction. So this is a model that they used for that ligand that I showed you before. One day, if we get our chiral products, we can make a model of our ligands. So pretty much just to give you a quick idea, we're working on these ligands. We want higher yields, higher anti-selectivity, shorter reaction time, so bigger, better, faster, stronger. And then we want to have low catalyst loads. We won't have to dump in a truckload of our catalyst to do this. We want less expensive ligands, so using amino acids is favorable there. Nobody's ever done this with an NH2 before, so that would be a really cool advance. And then in addition to this, I'm interested in not only this particular type of reaction, but developing novel chiral ligands for other reactions as well. So, each in the glove box. A lot of what we do looks like Largo, but some of it looks really cool. And there's Ryan in the stock photo with the series. Our reactions can be green, so sometimes the separations look kind of cool. And there's our short.